Alright, hi everyone, this is Kai, and I would like to talk about a constraint optimization of so-called Fermi orbital descriptors. So in order to introduce this topic, I'd like to start with the very general problem that we're trying to address here, and this is an optimization problem. So what we see here is on the x-axis the system size, and on the y-axis the number of variables, and I distinguish between two types of variables, and I want to explain them on the CH4 molecule. CH4 has 5 atoms, and each of these atoms has 3 Cartesian coordinates, so we have 15 coordinates to worry about when we want to optimize CH4. However, we know exactly that in CH4, the only thing that we need to care about is the distance between carbon and hydrogen, because everything else is determined by symmetry. So with that, we know that the number of Cartesian variables will continuously increase with system size, but the number of internal coordinates is going to be significantly smaller. In this case, it's 1 versus 15, and does not increase with system size as much. So that's the very general outline, and now I would like to say a few words about the method where we want to employ a strategy to include these internal coordinates. And the methodology we're using is the Fermi-Lifton orbital self-interaction correction, which employs the Purdue-Zunger self-interaction correction functional, which takes the standard Kohn-Sham density functional theory functional, depending on the total density, and subtracts an orbital-dependent self-interaction correction term. Now in FlowSig, the local orbitals that we're using for these localized one-electron densities are Fermi orbitals. And the general construction of the Fermi orbitals is given here, given by a transformation from the set of Kohn-Sham orbitals into a set of Fermi orbitals. And what I want to focus on are these highlighted AIs. And these AIs are called so-called Fermi orbital descriptors, or FODs, which are merely points in space that allow us to construct the Fermi orbitals from the set of occupied orbitals. So we have one of these FODs for every orbital in our system, and that generates a set of these points, which we typically refer to as the electronic geometry in our system. Now clearly the energy, the total energy, depends on our localized orbitals, and the localized orbitals depend on our FOD positions, so with that our energy is going to depend on these positions. And we have to find the optimal set of these points in space in order to minimize our energy. It turns out now that optimizing these FODs still remains one of the biggest challenges in FlowSig, and we would like to find ways to accelerate this optimization. Now I said that these FODs are points in space, but what we found over the past few years is that these FODs actually arrange in very recurring patterns given certain bonding arrangements and certain other structural motifs. And I'd like to show that again on the example of CH4. We have the atoms, carbon and hydrogen, and then in blue we have the Fermi. In green, we have the Fermi orbital descriptor position. And as we can see, this position is right in between the carbon and the hydrogen, right on the bond axis, and it describes the localized orbital corresponding to this bond orbital between carbon and hydrogen, which we have for all the carbon-hydrogen bonds. And if we then go to something slightly bigger, this is now C2H4, we see the same situation for the carbon and the hydrogen bonds, where the FODs are again right on the bond axis between carbon and hydrogen and correspond to a single bond. And in between the two carbon atoms, we know exactly that in C2H4 we have a double bond, and this is represented by two pairs of up and down FODs right in between these carbon atoms, oriented perpendicular to the molecular plane. So these patterns, we find these patterns in a whole lot of molecules, so we can now think about constraining the FODs to stay within these patterns, which could potentially allow us to accelerate the optimization of the FODs. In order to outline that a little bit more, I want to introduce the general idea of the constraint optimization of FODs. So what we typically do is we got to optimize all 3n degrees of freedoms for the FODs. So the Cartesian coordinates, which is what I'm going to call the unconstrained optimization. In this case, n FOD is the number of electrons or FODs in your system. And the idea is now to use a number of n internal coordinates by exploiting the local symmetries that I showed in the last slide of these FODs. Again, on the example of CH4, typically we have 1, 2, 3, 4, 5 sets of we have 5 FODs per spin channel, and each of these has 3 Cartesian coordinates. So in total we have 30 degrees of freedom that we have to optimize. However, the only thing that we actually have to worry about is the distance between these bond FODs and the carbon atom. So this reduces to 1. So that seems like a significant reduction and should simplify the optimization quite a bit. Now, I want to show how this reduction works for a bunch of molecules. And what we can see is that for the unconstrained optimization, the number of degrees of freedom to optimize ranges between, something between 40 and almost 100. While using these internal degrees of freedom, we reduce this by an order of magnitude easily, and we go down to a maximum of 7 degrees of freedom, which seems much easier to optimize. Now, of course, we want to make sure that we do not compromise our molecular properties when we do constrain the FODs. So what I want to do on this slide is to compare the unconstrained and the constrained optimization. First of all, in terms of how many steps does it take for the optimization to find a minimum. And then, of course, we have to have a look at the differences in, let's just say, the total energy and the atomization energy, and I choose a density-related property, that is the dipole, in these molecules to make sure that if we optimize in this constrained way, we do not compromise our molecular properties. So I want to focus first of all on these two columns. This is the number of optimization steps for the unconstrained optimization, and here we have the number of optimization steps for the constrained optimization. And as we can see, for the smaller molecules in our test set, we do reach convergence within a more or less reasonable amount of optimization steps. But we can clearly see that if we use internal coordinates, we reach this minimum significantly faster, easily by a factor of 3 or more faster. Now, for the bigger molecules, what we find is that reaching this minimum is actually pretty difficult and kind of hard to achieve. So you need easily more than 100 optimization steps to get there. But using the internal coordinates, we actually achieve this minimum within 20-30 steps. So this seems like a significant advantage to reach this minimum way faster. Now, having a look at some of the properties of our molecules, what I want to show you is the difference in total energy in millihartree. And as we can see, these total energies are pretty much identical. Even for SO2, we have a difference of 2.5 millihartree, which on a total energy of around 600 hartree is not the biggest difference. And we see a very similar story for the atomization energies, given here as a difference in millieV. And we see that these differences are very small. Even for the largest difference, which is again SO2, 68 millieV on an atomization energy that is easily in the order of 10 eV, doesn't make a difference, certainly not qualitatively, but even quantitatively. And now looking at dipoles, which I'm going to give here as a difference in debye, we see that even the dipole moments are virtually identical between the two optimizations, and even the biggest differences are tiny compared to the absolute value of the dipole moment. So what I wanted to show you today is a constrained FOD optimization by using internal coordinates. We do this by systematically constraining bond FODs, lone FODs, and core FODs. This significantly reduces the number of optimization steps. And we do this by imposing and then constraining local FOD symmetries. And I showed you that the molecular properties are essentially unchanged, which is of course critical for such an optimization scheme. So with that, I want to thank you all for your attention, and please don't hesitate to ask any questions.